Acid-base equilibrium, working with the acid dissociation constant Ka. In this tutorial, we will be looking at the acid dissociation constant Ka, calculating Ka from pH, calculating pH from Ka, doing a lot of worked examples, and then finally talking about polyprotic acids. Acid dissociation constant Ka. The equilibrium constant Ka expresses the extent to which a weak acid ionizes. There's two ways that we can represent the equilibrium expression for weak acids. The first is Ha reacting with water to produce the hydronium ion and the conjugate base, or Ha producing hydrogen ions and the conjugate base, where Ha is the general formula of an acid, a protonated acid, meaning that it contains a hydrogen ion, A-1, the general formula of the conjugate base, a deprotonated anion form, and the hydronium or hydrogen ion concentration. The equilibrium constant expression for a weak acid is represented by Ka is equal to the hydronium ion concentration times the conjugate base concentration divided by the concentration of the weak acid, or Ka is equal to the hydrogen ion concentration times the concentration of the conjugate base divided by the concentration of the weak acid, where Ka is the acid dissociation constant. Understanding the magnitude of the Ka value. The larger the value of Ka, the stronger the acid. Strong acids do not have listed Ka values as they fully ionize and favor the formation of products. In other words, the hydronium ion and the associated anion to a very large extent. The smaller the value of Ka, the weaker the acid. The denominator, represented by the concentration of the weak acid, remains mostly in a molecular form and does not ionize completely, so the associated Ka values are much smaller than 1. So if we look at this chart right here, we can see that our strong acids, which are listed at the top, have very large Ka values. In other words, they're so large they're not even listed because they're fully ionizing. Our weak acids, shown below, have listed Ka values, which means that they are weak acids. Write equilibrium expressions for the ionization of each of the following weak acids in aqueous solutions. So the first one that we have is bromous acid, HBrO2. The chemical equation for this would be HBrO2 ionizes to form hydrogen ions and the bromite ion. To write the equilibrium expression for this, we would say Ka is equal to the hydrogen ion concentration times the concentration of bromite divided by the concentration of bromous acid, where the top concentrations are relatively small and the bottom concentration of our weak acid is relatively large. So our Ka value is going to be small. Let's look at another example. This is HC3H5O2. This is propanoic acid. The chemical equation for this would be HC3H5O2 ionizes to form the hydrogen ion and the propanate ion. To write the equilibrium expression for this, we would write Ka is equal to H+1 times the propanate ion concentration divided by the concentration of the propanoic acid. Again, the concentration of our hydrogen ions and our propanate ions are going to be relatively small compared to the concentration of the propanoic acid in its molecular form on the denominator. So this leads to, again, a small Ka value. Calculating Ka from pH. Lactic acid, HC3H5O3, has one acidic hydrogen. A 0.10 molar solution of lactic acid has a pH of 2.44. Calculate Ka. Our first step is to write the equation for the equilibrium system. So we would write HC3H5O3 ionizes to form H+1 plus C3H5O3 minus 1. The next step is to write the equilibrium constant expression. So we would write Ka equals our hydrogen ion concentration times the concentration of the lactate ion divided by the concentration of lactic acid. After we have our equilibrium constant expression written, we'd go on to step 3, and from the given pH, calculate the hydrogen ion concentration. So we would start with pH is equal to the negative log of our hydrogen ion concentration. We would rearrange our formula to find the hydrogen ion concentration, which is equal to the antilog of the negative pH. We would plug in our numbers and then solve for our hydrogen ion concentration. In this case, it's 0.00363 molar. We're going to take this number and use it on the next slide. Our next step is to construct a rice table to determine the concentrations of the species involved in the equilibrium. So we have our rice table, we have our lactic acid formula, the hydrogen ion formula, and the lactate ion formula represented in the last column. Initially, we start out with 0.10 molar of our weak acid and no hydrogen ions and no anions. The change here is going to be ionizing some of this lactic acid to form hydrogen ions and some of the anion. From the previous slide, we know that the concentration of the hydrogen ion is equal to 0.00363 molar. So we can plug that into our values in the change section of our rice table. So 0.10 minus 0.00363 molar. And then we'll have the concentration of our hydrogen ion represented here. And because there's an equal ionization of hydrogen ion to anion, both of these numbers will be the same. Because we have our X value for above, we can solve for the equilibrium values. For the lactic acid, that's going to be 0.09637 molar. And then we'll have our hydrogen ion concentration and our anion concentration. Now we can move on to step 5, which is insert the equilibrium concentrations into the expression for Ka. So we'll have Ka is equal to our hydrogen ion concentration times the anion divided by the concentration of the weak acid. Then we'll plug our values in. So Ka is equal to 0.00363 squared, because that's representing these two values right there, divided by our equilibrium concentration of our weak acid. This includes the X. So in this first scenario, we're subtracting the 0.00363 molar, where Ka is 1.37 times 10 to the negative 4. Now, considering that this is two significant figures, the Ka value would be 1.4 times 10 to the negative 4. Let's compare that to if we disregarded this value for X right here. So we would have Ka is equal to our equilibrium expression. Then we have Ka is equal to, and then we'd plug our values in here, with the exception of we're just going to use the value of 0.10 in this scenario in disregarding this X value right here. In this case, like I stated before, we're ignoring the X. So we're disregarding the 0.00363 molar, and our calculated Ka is 1.32 times 10 to the negative 4. To two significant figures, the Ka value is 1.3 times 10 to the negative 4. So there's a very small difference between these two Ka values if we ignore this X being subtracted from the concentration of our weak acid. So the X value here is negligible relative to the initial concentration of our weak acid of 0.10 molar. That's something to keep in mind as we do more of these problems later on in the video, and we'll go through the calculation of how you exactly know whether that X value is negligible or not. Calculating pH from Ka. To calculate the pH from Ka, the following is necessary: a value of Ka from a vetted resource, the initial concentration of the weak acid. So for example, calculate the pH of a 0.095 molar propanoic acid, HC3H5O2, where our Ka value is 1.3 times 10 to the negative 5. So step 1 is to write the equation for the equilibrium system. So HC3H5O2 ionizes to H plus 1 plus C3H5O2 minus 1. Then we're going to write the equilibrium constant expression. Ka is equal to the concentration of H plus 1 times the concentration of C3H5O2 minus 1 divided by the concentration of our weak acid. The next step is to use a Rice table to express the concentrations that are involved in the equilibrium reaction. So again, here's our setup for our Rice table. Initially, our concentration of propanoic acid is 0.095, and our concentration of hydrogen ions is going to always be 0, and then our propanate ion is going to also be 0. To represent the change, we're going to write 0.095 minus x plus x and plus x. And then we need to go on to step 4. We can't plug in x yet because we have not calculated x at this point. So we're going to substitute the Ka value and the change expressions into the equilibrium constant expression. So we're going to write Ka is equal to the hydrogen ion concentration times the propanate ion concentration divided by our concentration of propanoic acid. We're going to plug in our values. So Ka is equal to 1.3 times 10 to the negative 5. That's going to equal x times x divided by 0.095 minus x. This leads to step 5. So the expression in step 4 leads to a quadratic equation, which we could solve using the quadratic formula. We can also simplify the problem by noting that the value of Ka is quite small. As a result, we anticipate that the equilibrium will lie far to the left and that x will be very small compared to the initial concentration of propanoic acid. Thus, we can assume that x is negligible compared to our initial concentration. As a result, we're going to take our expression that we wrote on the previous slide. 1.3 times 10 to the negative 5 is equal to x times x divided by 0.095 minus x. So x is very small and we will disregard it. Then we'll rewrite our equation. So 1.3 times 10 to the negative 5 is equal to x squared divided by 0.095. We'll rewrite this equation solving for x. So x squared is equal to 1.235 times 10 to the negative 6. We're going to take the square root of both sides. And if we take the square root of both sides and solve for x, x is equal to the hydrogen ion concentration, which is 1.11 times 10 to the negative 3 molar. From there, we can solve for pH. So we'll use the pH formula. pH is equal to the negative log of the hydrogen ion concentration. We'll plug in our value of our hydrogen ion, and then solving for pH, we find pH to be 2.95. And we can stop right there. We do not need to go back to our Rice table and complete that because we already know the value of our Ka. The whole point here was to find this pH value, which we succeeded in doing. As a general rule, if the quantity of X, our hydrogen ion concentration, is more than 5% of the initial value of the weak acid, the quadratic formula is necessary to calculate the hydrogen ion concentration. Now, on the AP exam, they're not going to do this to us, but it's good to know this formula. So we'll use the formula percent ionized of propanoic acid is equal to our hydrogen ion concentration ionized divided by the initial concentration of our weak acid times 100. If we plug in our values, our hydrogen ion concentration of 1.11 times 10 to the negative 3 molar divided by our initial concentration of our weak acid, which is 1.095 molar times 100, and then our calculated value is 1.11%, which means that the percent of hydrogen ions ionized is 1.11%. Therefore, the X value is negligible relative to the initial concentration of our weak acid of 0.095 molar. using the quadratic formula is not necessary. So this is a really good formula to know how to use to check your work. Calculating pH from Ka. Another example. Calculate the pH of a 0.100 molar hydrogen chromate HCrO4-1 ion. Our Ka value is given as 3.0 times 10 to the negative 7. So step 1 is to write the equation for the equilibrium system. So we would write HCrO4-1 ionizes to form the hydrogen ion and the chromate ion. The next step is to write our equilibrium constant expression. So Ka is equal to the hydrogen ion concentration times the concentration of the chromate ion divided by the concentration of the hydrogen chromate ion. So step 3 is to use a Rice table to express the concentrations that are involved in the equilibrium reaction. So we have our Rice table set up. Our initial concentration of the hydrogen chromate ion is 0.100 molar. Initially, we do not have any of the hydrogen ion or the chromate ion. We'll put in our change expressions. So 0.100 minus x, and then plus x and plus x. And then we'll take those values and we will substitute the equilibrium concentrations into the equilibrium constant expression and solve for the hydrogen ion concentration. So we have our equilibrium expression. We will substitute in our Ka value, which is 3.0 times 10 to the negative 7, is equal to x squared. And then we're going to divide that by 0.100 because we're going to assume that x is small and we can disregard that. We will rearrange this expression to solve for x squared. So x squared is equal to 3.0 times 10 to the negative 8 when we multiply these two values together. If we take the square root of x squared and the square root of 3.0 times 10 to the negative 8, our x value is equal to our hydrogen ion concentration, which is found to be 1.73 times 10 to the negative 4 molar. And once we have our hydrogen ion concentration, we can move to the next step, which is calculating our pH. So to find the pH, we're going to use our pH formula of pH is equal to the negative log of our hydrogen ion concentration. We'll plug in our value that we calculated on the previous slide for our hydrogen ion concentration of 1.73 times 10 to the negative 4 molar. In solving for pH, we find it to be 3.76. So our next question is, can you disregard the x? So we'll use the formula percent ionized of hydrogen chromate ion is equal to the concentration of hydrogen that was ionized divided by our initial concentration of our weak acid times 100. We'll then plug in our values. So our concentration of hydrogen that was ionized was 1.73 times 10 to the negative 4 molar divided by our initial concentration of the acid, which is 0.100 molar times 100. And we find that our percent ionized is 0.173%, which means that we can absolutely disregard the x value. Polyprotic acids. When acids have more than one ionizable hydrogen atom. So for example, the hydrogen atoms in sulfurous acid H2SO3. So we can write the equation H2SO3 ionizes, and here's our first hydrogen ion forming HSO3-1, and that has a Ka value of 1.7 times 10 to the negative 2. Our next equation is HSO3-1 ionizing to remove the second hydrogen ion and forming SO3-2. The Ka value for this equation is 6.4 times 10 to the negative 8, where Ka1 is the equilibrium involving the removal of the first proton of a polyprotic acid, and Ka2 is the equilibrium involving the removal of the second proton of a polyprotic acid. And we notice the difference between these two values. General observations. It's always easier to remove the first proton from a polyprotic acid than the second proton. Ka values become smaller as successive protons are removed. Ka values for successive losses of protons usually differ by a factor of at least 3. Almost all of the hydrogen ions in the solution come from the first ionization reaction. When given multiple Ka values, use the largest of the Ka values and disregard the smaller Kas. The smaller Ka values will oftentimes be insignificant. So what did you learn? We talked about the acid dissociation constant Ka, calculating Ka from pH, calculating pH from Ka, a lot of worked examples, and finally a little bit about polyprotic acids. Need more help? Feel free to contact me. Have a great day.